Hi.
Hi, Dr. Zhu.
Hi, Goi. How are you?
Good. How are you? You look a little bit different from the photo.
How's it going?
Things are well. How's everything going? It's pretty early right now in Sydney,
Yeah,
right?
it's 6:30
Yeah.
a.m. in
Okay.
Sydney. It's
Okay.
a bit early, but no worries.
Yes. Yeah. Sorry to make you get up early, so early. It's relatively fixed time for our seminar in USA time. So, but probably we wait another 1 or 2 minutes, and then we can get started. And some usually students get in a little bit, a couple minutes late.
Okay.
Yeah.
So I noticed that there might be some undergraduate students.
Almost no undergraduate, actually.
Okay.
Most are graduate students.
All right.
Yeah. So feel free to teach something like a little bit more advanced, not too advanced, not too deep, maybe.
Okay. Yeah. Because I don't know how. I mean, what materials are suitable? So I just grab a few our recent works.
Yeah, that's great. That's great. I saw your recent work, and that is totally a good fit. And for our topic, so we are in imaging science, and so everything we do in the department is about imaging. So I saw you published in the ECCV, ICCV, and the last year CVPR as well. So I'm pretty sure what you are going to talk about will be pretty related to what we are doing, and I think they should be good fit.
Okay, thanks.
Yeah, you look a little bit different from the photo. When did you capture this photo? 1 year, 2 years?
A few years ago. Yeah.
A few years ago. Oh, I don't.
Yeah, Sydney has been locked down for a while.
Okay. Okay, this is the first year or second year for your current faculty position?
Second year.
Second year. Okay. So I think we can get started actually. So because I will need to give a brief introduction, and then perhaps people will get in slowly, and it's recorded right now. So it's our great pleasure to have Dr. Linchao Zhu and to give us a talk. And Dr. Zhu is an assistant professor in University of Technology, Sydney. His research includes computer vision, machine learning, and visual representation, and video learning, and supervised learning, transfer learning, those kind of different machine learning algorithms used in imaging and used in videos computer vision. And he received his PhD from University of Technology, Sydney. And obtained his bachelor degree in Zhejiang University in China. And he has published many papers and in TPAMI, IJCV, CVPR, ECCV, ICCV, those top conferences and journals. And in recent time, and he also has participated several international competitions in CVPR or some other conferences, and when ranked first and in multiple competitions. And in this year, he also received a Google Research Scholar Award, actually, which is very prestigious. And I would like to thank Dr. Zhu again for giving us a talk. And now, Dr. Zhu, is your stage.
Thanks, Corey, for the introduction. Thanks, everyone. It's my pleasure to give a presentation here. Let me share the screen. Just a second. Yes, can you see the screen?
Yep.
Sure. Okay. So I will briefly talk about like a few works we've done in visual recognition or visual representation learning, basically more focused on the practical perspective. And if you have any question, please feel free to interrupt me. So I think we are in a small meeting group, and feel free to unmute yourself and ask questions if you have if you have anyone. Okay, basically I will start with the overview. I will talk about when you have a large amount data set and you will get noise. So I will start with noise robust modeling, because one of the way towards practical visual representation learning is to do noise robust learning. And the second, I will talk about learning from weak supervision, because when we are talking about web data, those web images or web videos are noise annotated, and they are also weak supervisions. For example, there are text video correspondence, there are text audio correspondence, and sometimes the text and the audio are not well aligned with the images or the videos. So the correspondence or the supervision is weak. And the third part, I will talk about adaptation, because in the real world, an agent or the model has to be adapted very fastly to a new domain. For example, you have one agent trained on a, for example, kitchen domain. How can you adapt it directly to a new domain, for example, in the self-driving car scenario? Is it possible, or what should we do to make it happen? And efficiency is one of the key issues in this task, which is, I mean, my main topic is towards practical visual representation learning, and that you have to have your model very efficient so that the model can be practical in the real world. Okay, so let me start with the noise robust model. Okay, and the noise labeling data, or the problem, or the learning from noise labels problem, is to give you a very noise data set, and the data set may be annotated by crowdsourcing platforms, and maybe, or the data set may be collected by search engines. But anyway, there are some noises in the data set. For example, some pixels are not well annotated for segmentation tasks. Some bounding boxes is not well annotated for the object detection task, and some labels are mislabeled for the action for the classification tasks. So how can you learn a robust model that generates well given the noise training set, but it can generate as well in the clean test set? So there are a few works. For example, there are works focused on regularization. How can you avoid overfitting on the noise labels? Because you know the deep neural networks are usually very powerful. They can fit any labels, any kind of data. So we need some regularization techniques to avoid the overfitting over the noise labels. And another way is to do label cleaning. If you have some noise labels, how can you automatically clean or correct the labels so that we can get cleaner and cleaner labels for our training process, and the network will automatically not going to overfit the noise labels. Another way is to do reweighting. Reweighting is, for example, to downweight the label of the loss weight of the noise labels, but to increase the weight of the clean labels. That's the reweighting task, a reweighting method. So I will briefly talk about meta-learning, because I will introduce one method that use meta-learning to deal with noise labels. And there are a few works that has been proposed to do noise labels using meta-learning method. One is L2R, learning to reweight, published in ICML in 2019, and the other is the MW net, MetaWeightNet, published in NeurIPS in 2019. So basically, these two works use meta-learning. And in meta-learning, there usually is one model. For example, here is an example of the meta-learning paradigm to deal with the noise data. There is a learner and there is a meta-learner. And then the meta-learner will be able to receive some clean data or the reward data to get some feedback from the reward data about the noise condition of the training data. For example, the learner here will get will be trained to fit the training data, but there are some parameters in the training in the network that need to be optimized by the meta learner, and these parameters are usually called meta parameters, and these meta parameters in the reweight condition is usually to reweight the loss. So I will give you an example here. For example, this is usually the training objective to optimize one the parameter of W, which is the network, the main backbone, the parameters of the main backbone. For example, here is the training loss, and when you when you're given an example, you can get the loss over here, right? You can get the loss over here, and as I mentioned, for the reweight method, there usually a weight here, V here. V is the weight to reweight the loss term, and the weight is parameterized by theta here. Theta is a small network or any network, and given the V is the input to the V is a loss, and the network will automatically decide whether this is a clean example or noise example. So this is the loss to this is the way to optimize W here. So the first is to optimize W on the noise training data set, and the second is to optimize the meta model, which is theta here, which is the parameter theta here, using a clean validation set or a clean reward set. So the second part is to optimize theta. So there's admin here, and we use some data from the validation set to optimize the theta here. So this is the loss for optimization of the theta. The problem with the meta-learning method is that it's not efficient. So you can see here, this is, as I mentioned, this is the one paper published in Europe in 2019. And you can see that for only like 50K images using 4V100 GPUs, it takes about 100 hours to train the model. So it's not quite scalable. And you can see there is a small performance drop even when you train at around 85 hours. I will explain the performance drop shortly. So it's not efficient. If you have an even larger data set, then this model is not scalable. And when we dig into the model, like for forward, backward computation time, and we can see that these are the steps: virtual forward, virtual backward, meta forward, meta backward, actual forward, and actual backward. These are the 3 stages. 6 stages we divided the whole training process, and we can see that meta backward takes a really large percentage of the whole training process. So this is a meta weight network, one of the baselines, and we can see here the meta backward takes above 90% of the training time. So our motivation is to reduce the training time of that part, and our motivation is quite simple, which is to simply reduce the number of gradient updates in the steps. So I'll briefly introduce the overall idea, and I think it's quite simple. And if you don't understand, you may just ask questions. So here, this is the training process. Virtual train means we just train the model, update the W. W is the weight of the backbone. For example, give you an example, X train, and we forward this example into multiple layers. It's whether it's convolution or linear layers. We can get an activation here, and we can get the loss over here. That's a loss. For example, typically the loss can be cross entropy loss. And there is a weight module. Weight module will take the loss and output a weight. Okay, so basically, this is the weight outputted by the meta model, and you can update the W by gradient descent. So single step backward, a single step gradient update using this operation. And alpha is the step size, and I think this equation is easy to understand. And by backpropagate the loss over here, we can get the gradients. But when we are using the gradients, we simply aggregate the gradients of each layer to be G sub 1 hat, G sub 2 hat. So each layer has a gradient, and we aggregate the gradient and denoted it as G1, G2, G3, GL. And I will talk about the gradient annotation very shortly. So this is the meta. This is the virtual train process. We have a forward and we have a backward update. Okay, this is the validation set, and we will do a meta train forward. And this is to update the parameter theta. And you can see we are using an example from the reward dataset, and we forward the example to the network again, but the network has been updated to be W1 hat, and W1 hat is the updated weight of the previous step 2, right? Step 2, we got W hat, and here we use W hat as the current parameter, and we use X as the input and forward the input to the network, and we can get a loss L val. And the next part is the tricky part. So when we are doing the meta gradient update, we need to back propagate the loss over those layers, right? And we found that the computational cost is quite extensive during the meta update, because you have to calculate this second gradient, and it's not cheap, it's quite expensive. And our goal here is quite simple. When you backpropagate the gradient, what if we can simply stop the propagation using a sampler here, so we call it faster meta update strategy, using the sampler here, that the sampler will automatically decide whether we need to backpropagate or not. For example, here R2 equals to 0, which means that this layer, we don't need backpropagation. We don't need backpropagation, and for this layer, again, we don't need backpropagation. But for this layer IL, we will backpropagate the gradient. We will backpropagate the second gradient to this parameter, okay? And then everything will be accumulated to update the parameter theta. So basically, if we don't use the sampler, the whole path is like backpropagate to the very end, and then you backpropagate until the very top. So that's the calculation of the gradients. But if we're going to use the sampler, we will only need to backpropagate a few layers. So that's why we can save the time. So the idea is quite simple. We use a very simple sampler to decide the importance of the gradient. And then this sampler will decide whether we will do the propagation over in this layer, and whether this gradient will be accumulated or not. Okay, so this is the idea. And after updated the theta, we can get theta prime here, we can get theta prime, and we will use theta prime to update the actual model, and then the model will be updated. So this is basically the process. I think I'm not sure it's clear or not, but if you have questions, you can ask. And this is our gradient sampler. So this gradient sampler will take the average of the gradient and just input to a very small network. Here is 2-layer network. The hidden size is 1 to 128, and then we will use the Gumbo sampler. The Gumbo softmax trick to output 0 or 1. One is that the gradient will be accumulated, but 0 is that this gradient will not be accumulated. And this is the results, and we get very promising results on a few data sets. For example, here on CIFAR 10 and CIFAR 100, we tested on different noise rate. So 20%, 40%, 60% are the noise rate, means that how, for example, 40% means 40% of the data noise labeled. Okay, the matter with the net, the MW net is the baseline, and you can see that this baseline is quite expensive. It took one per training iteration takes almost 1 second, but we reduced the cost, reduced the computational cost by more than 3 times. So we can get faster training. But you can see here, the interesting part is we can even get a higher accuracy. This is very interesting, and this surprised us as well. Why, if we just start the gradient accumulation and we didn't do anything else, why we can get a higher accuracy number? This is very interesting, and we did some testing, and this is the training curve. The curve on the test, the curve of the accuracy on the test set, and you can see that this is our model consistently have higher accuracy over the training time, and this is the loss as well. The test loss is consistently lower over the training time. Why this happens? We did some tests, and we found that the meta gradient, norm of the variance of the meta gradient has been significantly reduced. For example, you can see here, this is the random, just a random initialized the network, and we calculate the gradients, the meta gradients on the of the network. And when we're using meta with net, we can see the gradient, the variance of the gradient is much higher. And this is because when we have a deep network, for example, like 18 layers or 50 layers, the gradient will have to propagate into the very bottom, and the gradient noise, gradient variance will be increased a lot, because those there are uncertainties, and when you are propagate deeper, and the uncertainties will be accumulated. So that's why meta with the net has a very high gradient variance, but this is our gradient variance, and you can see that we are quite stable. The gradient is very stable because the sampler may learn to ignore those bottom layers and select those high layers, and in this way we can get a stable gradient. And there are some research found that if you have a stable training process, you may have a better accuracy. But this is not validated or proved yet. I think if you're interested in the gradient variances during the training or the training stability, you may look into this. We cited one paper in our paper. If you're interested, you can have a look. And this is the comparison with the state-of-the-art. We compare to a few methods on CIFAR 100, CIFAR 10, web vision, and LSVRC data sets. And we also trained on a noise web, recently introduced the controlled noise web labels data set. And you can see that we consistently improve the baselines or even the state-of-the-art across those benchmarks. I will just ignore those boring numbers. And this is another experiment on long-tailed training. When you're dealing long-tail data, there is some imbalance there, and reweighting is one of the mechanisms to reweight. So we apply our method to deal with biased or long-tailed imbalanced data sets, and we can receive a consistent improvement over the baselines. Okay, so I will just draw a quick conclusion of the famous framework, and you can see that we successfully reduced the meta training process by two-thirds of the training time, and we achieved the state-of-the-art method on both synthetic noise labels and realistic labels. And we also proved that this method can also be used in long-tail classification or any meta-learning method that requires meta update. And I think in the future, our framework can be extended to other methods as well in different tasks. Okay, any questions so far? No. Okay, so I will next talk about.
I have a quick question. So you mentioned your framework is good for long-tail classification issues. So do you have a intuition that how many layers and how complexity the network is well suited for your new training framework? And another thing is something like how complex you think that your framework will be pretty efficient for training or bring the most effect in enhancing the training result and reducing the training time.
Okay, so on the long tail data set, and we simply start with the baseline, which is meta-weighted net with the cross entropy loss. We just start with this baseline because meta-weighted net can also directly be applied to long tail classification, where you add a reweighting term here in the long tail classification. The setting is quite different, and thanks for pointing out, is that we reserve a balanced data set. We reserve a balanced data set, but the example per but not the number of examples per category is only one. So we only reserve one example per category to serve as the reward data or the validation data. So for the other part, for the training, for the other training part, we keep the same. We didn't do anything different in our for example, in noise label classification tasks. And so we didn't do anything with the training at all, but only to introduce the layer-wise gradient sampler. So I think it might prove that this framework is feasible to apply to different tasks.
Okay, yeah, that is very interesting. It's actually less is more. actually here.
Yes, yes. So this, I think this is a very nice catch. And there are some works that are really interesting gradient, gradient study of the gradient, for example, gradient normalization. How can we stabilize the training or even accelerate the training? We don't need 100 epoch. Can we do like 10 epoch so we can get a better or comparable performance? So these works are also very interesting. The gradient operations, for example, reduce the norm. How can we use some layers to update? And I think this sampler can inspire a few other future works in this area as well.
Sure. Yeah. Actually, there is another follow-up question.
Yes.
Is from our student, and did it affect the training time? Do you have to change any parameters?
So we, for example, for the results here, we use the same hyperparameters as the meta with net. So we use the same parameters with the meta with the net, but different data sets, they have different parameters. For example, CIFAR-10 is quite small, and the size is also, the input size is also different. But we didn't change the parameters for training compared to the meta with net.
Okay.
Okay. So I will just,
yep.
So I will just move on to the next part. So when you're dealing large amount of web data, web videos or web images, another concern. So we talk about noise, right? The images are not well labeled. Another concern is that we may not have sufficient annotators or sufficient funds to annotate the data set. When you have millions of images, it's even impossible to add a label, add a single label. So it's quite expensive. So we have some works annotating the pixel-wise segments or pixel-wise labels, semantic labels. So you have to draw the boundaries, etc. It costs one labor almost 1 hour to label a 1024 by 1024 image. So this is very time consuming. So how can we learn from weak supervision? So I will just give an example to learn from text, video and text correspondence. So for example, here I give an example of the instructional video. So when you're watching instructional videos, the instructor will sometimes talk when he or she is acting. For example, this guy is like putting some black pepper into a pan, or I'm not sure, put some black pepper into something, right? He or she will say some words, some keywords when he or she is doing the action. So you can get the weak supervision of the, for example, an image or a video, a short clip with a description here, and description can be extracted using automatic speech recognition. So if we are dealing with instructional videos, and we can get very good weak supervision from the data itself. So we don't have to manually annotate it, okay? But the weakness of these instructional videos is that the annotation is quite noise, but we didn't deal with noise in this case. By noise, I mean sometimes the instructor may say something not relevant to the image content, and sometimes the descriptions and the actions are not well aligned. So there are some noises, but we didn't consider noises at this stage, because we just want to assume that those correspondence are well aligned, and how, if we are using this alignment, how can we design model to learn the video and text correspondences. So this is one paper published in ICCV 2019. They introduced 100 million clips of instructional videos, and they just simply use a very simple. The loss is quite simple. You can see here, this is the similarity loss, and this is just the cosine similarity, and you can see that they use a very simple margin loss, and surprisingly they train it, and it works very well on many downstream tasks. So their framework is quite simple here. The visual part is going to the video network, and the text part is going to the text network, and they train a very simple ranking loss. So, but this whole network, this whole model generalizes very well in many downstream tasks. So this inspires us to make it more effective. So we're going to use BERT for training, and I assume that you might familiar with BERT, and the idea of BERT is quite simple. So they would like to do language modeling, and when they do language modeling, they use an idea called, for example, masked language prediction. Sorry, it's a prediction, not mask. For example, here is the description here. The man went to somewhere. He bought something of a milk. So if you see this input, you may, as a human, we may automatically generate some description here. Okay, given he bought some milk, the man may go to the store, right? And bought a mask 2 of milk. The mask 2 might be a gallon or other quantity. So as a human, we can automatically predict the words from the context. How can we but the model can the model predict those the words from the context? If the model can predict the words from the content, then the model learns the words very well. So this is the motivation. And the next task is to do next sentence prediction, whether this sentence is adjacent to the next sentence. So the idea of BERT is very, very simple, but they work very well. And I will talk about the idea in my last slides as well. So there are a few other works that would like to move move text modeling or language modeling into, for example, image text modeling and video text modeling. So this is the idea. The BERT model, given the 2 sentences and some tokens are masked, and the model is to predict, for example, the tokens at the end. So if the model can predict the tokens very well, then it means that the model learn the context and learn the meaning of the word. And for image and text descriptions, for example, there's a photo here and there's a description here. We can do the same. And for example, mask some regions or mask some images, and then we mask some tokens. If we can predict the images and predict the tokens, then we might assume that the model learns the video of the image and the video, the image and text correspondences. Okay, there's one previous work also published in ICCV. Their goal is to just use the idea of BERT and apply it to the video and text domain. So their idea is quite simple. Given description here, given a visual sequence here. We randomly mask given a probability here. Randomly mask some tokens. For example, here some beef is masked. Some here the word steak is masked. The goal is to predict each token. Place the steak in the pan, but steak is not appearing in the input. Can the steak be predicted using the video BERT model? And the tricky part is the visual model, because when usually for the token we can just classify it, but for the image, for the image there's no labels for the image. One way is to do regression, feature regression, but it is proved to be not very effective when training the model. So the video BERT model just simply do hierarchical clustering over the images and then use the cluster center as the label of the frame. So they first do hierarchical clustering and then use the cluster centers as the label, so they can directly do classification. So they don't need to do regression, and they found it works pretty well in many downstream tasks. But the question is that when you do hierarchical clustering, the model may miss some information, because when you do clustering of the whole, for example, whole steak, you may miss some interactions, right? Because you just, the vocabulary size is, the number of centers is fixed. Sometimes you cannot cover a lot of information in one frame, because there's even many things going on in one frame. So one label might be not sufficient to cover everything in that frame. So our motivation is to improve the model simply by decoupling the word and nouns. For example, if you have one frame, one clips, rotate shrimbles, we try to divide the description into the action and the objects. For the action here, rotate shrimble is rotate, and for the object, for the object part, it's shrimble. So if we can use language processing toolkits to decouple to extract the verbs and extract the nouns. And then we try to develop a new framework that can predict the verbs and predict the nouns separately. So as I mentioned, for the BERT model, their goal is to use contextual information to predict some masked information, to masked tokens. So if we can automatically, so if we can input more information in the input tokens, for example, we have action tokens and we can have region tokens, then it might be helpful for the model to uncover the relation between, for example, this region to this region to shrimbles, right? So this is the general idea. Usually for the BERT training, you usually have a clip level feature, and then you have a language description. Here you feed everything into the BERT model, and then you can do prediction. So our idea is to decouple the clip level feature into action features and region features. And the action feature will be the action representation, and the region feature will be the each proposal, region proposals. So as I mentioned, that this region information may help the model to align the visual feature to the shrimble, right? And this action feature may help the model to correspond to the whole sequence, the whole action sequence to the description of rotate. Okay, so this is our framework. I'm afraid I don't have enough time, but this transformer idea is quite straight as well. We have string 3 streams of transformers, and we apply the interaction at the input to do the interaction between the action and the word and action and then the visual regimes. So I will just skip this. So the idea is straightforward. We use a 3D network to extract the features of the clip, and we use region proposals to get the region features, right? And the idea, so this is the input token, and the idea is to input the clip features as the action. So we have an action token here, and to add the region features as the region token. And we also add position embedding for the spatial regions. And this is the segment embedding and the normal position embedding. I will just ignore this. And for example, here a description is masked, and the goal is to predict it's a shrimp. For example, this clip is masked. Can you predict the verb? And if this region is masked, can you predict the noun? And there is a cross-matching, cross-modal matching to model the correspondence of this clip and this clip. So the idea is quite simple. So we evaluated on the same data sets, and we pre-train our model on how to 100 million clips, on a how to 100 million data set, and it has over 100 million clips and 1.2 million videos. And we evaluated many tasks on different video text applications. So this is the results, and I'm afraid I won't cover the results in detail, but anyway, we get good performance for the video and text downstream tasks. So I will just summarize everything. We pre-train one model using some predefined losses or predefined training tasks, and then we apply it in many downstream tasks to demonstrate that given sufficient videos and a good pre-train loss or pre-train task, we can get pretty good generalization over downstream tasks. Faster generalization is quite important, but I'm afraid I don't have enough time to cover everything. But I will simply talk about maybe this work. I'll briefly talk about this work because this is related to my conclusion. So I will just ignore my previous work. So basically the idea of transfer learning is to transfer knowledge from one domain to the other domain. And this is an example of the transfer idea. If you have a source domain, you want to adapt your trained convolutional neural network on target domain. And the source domain and target domain may have some overlap. So some previous works would like to select a subset of examples for the training process. So for example, the target domain is for bird classification, then you may select more bird images for training because this is more related to the target domain. So there are some works that would like to do the sampling of the training so that that can be adapted to the more well aligned with the target domain. So so our idea is to, again, using the idea of meta learning. So how can we automatically decide the weight of the example in the training set using the feedback from target data set? For example, can the agent automatically decide the weight of the example? For example, my target validation target data set is to do some like bird. Can we apply a high weight for the bird and a relatively small weight for some irrelevant images? Can we do that? If we can do that, we can train it in an end-to-end way. Okay, so this is the framework. I'll just briefly introduce the framework on the right part. Again, for the noise, similar to the noise pipeline I just introduced, we have a source data set. In the noise sample, we have the training data set and the reward data set. And for this application, we have a source data set and a target data set. And the target data set is the domain you want to evaluate your model performance. And the training set is where you have large amount of training data for training. So we basically introduce two parameters. One parameter is to decide the importance of each sample, and the other parameter is to add the importance of the whole domain. So we have two parameters, and the reward here is come from the target data set. So we will train our model on the training set, and we will evaluate our model on the target data set. And on the target data set, we will get the reward, and our reward will be used to optimize the policy model here, and the policy model will subsequently optimize the parameters of the two parameters, the instance importance weight and the scaling weight. So basically, I will show you some interesting findings. And this is quite interesting. So here we show some application on classification over DTD dataset. So DTD is the dataset here. Those are texture datasets. So it's not normal object datasets, or all the images are textures. For example, there are some blocks here and some creamy, there's dotted lines here. So how can we optimize our model so that we can use large amount of data in the ImageNet or even larger data set to facilitate the training of texture images classification? So we tested, so the idea is can we select some relevant images in the training set, and we create a new subset to the target domain that this subset is more relevant to the target domain, and can we improve the adaptation performance? And we can find that we achieve that. For example, when we are using the whole training set of the DTD dataset, we can improve fine-tuning and random initialization with a large margin. When the number of categories is small, when the images are small on the DTD dataset, we can even get a higher improvement. And surprisingly, we can even get a small improvement over the Checksburg datasets. Chest arrays are not general objects, but we find that using our technique, we can have a higher MAP, I think, compared to the baseline, compared to the fine-tuning baselines. And I will show some very interesting visualizations. For example, when we are going to train our model on bird, so the target domain is bird, and these images are sampled from the training set that have a very high weight. So we can see that some bird are assigned with a high weight, and some bird are assigned with high weight, and some background are assigned with a high weight. But this is a completely different category, right? So this is the category of valley in ImageNet, but this example is assigned with a high weight. And we believe that for the bird domain, there is some background about some valley. So valley information is also important for the target bird classification. And another example is the cars. A car's like 4 wheels, and we found that even some wheels here helps to capture the feature of the car. So this is quite interesting. And for the DTD dataset, it's even more interesting. For example, for the DTD dataset, there are some class called matted. So we need to train a model to classify this image as matted. So the label domain is totally different. How can we automatically learn something or improve the adaptation using ImageNet classes when we find that this category has a very high importance way, because I think this furry thing is related to the matted. And another example is here. Those are shirts that has lines, and then we find this chicken or this prairie chicken has a very high rate, and this has a very high high weight. And this is quite interesting because this, if you put this image into this domain, it would definitely be classified as lined. But in the ImageNet dataset, it is classified as a chicken category. The domain is very different, but the low level similarity, they share some low level similarities as well. Okay, so I was just quickly drew the conclusion. So you may notice that I talked about meta learning a lot, and in the first part I talked about when you are dealing with noise data, you can use a reweight, and we can use meta learning to do the reweighting using a reward data set. And in the adaptation part, I also introduced meta learning, right? Because you can automatically learn the sampling strategy, how to sample or learn to sample, learn to reweight the source examples using a meta learning strategy. You may not notice that in the second part, I talked about video text pre-training. This is also can be regarded as a meta learning because you didn't directly optimize on the target. Sorry, you didn't directly optimize on the downstream tasks. Instead, you learn a new task, and this task is very relevant to the target task, and this can be regarded as an outer loop. So the pre-training can be regarded as an outer loop, where you just learn to generalize across tasks, learn to train the model that might be very helpful. So the model you train might be very skillful on the downstream task, but you didn't directly optimize on the downstream tasks. So in the outer loop and the inner loop way, you can regard the pre-training as an outer loop and the downstream evaluation as an inner loop. And this also is a meta learning paradigm. So again, I think I talk about practical visual representation learning. We talk about noise. We talk about adaptation, and we talk about learning from weak supervisions. And I introduce almost one simple framework, which is the idea of meta learning, to train, to reweight, to adapt, and to generalize across different tasks. So I think if you find it interesting, you may apply or may think about this idea even deeper and analyze or even apply it in your own work as well. The last word is about efficiency. Efficiency really matters because meta learning is not very efficient. Can we improve the efficiency using grid sampling, or can we reduce the number of forward networks? Because when you do meta learning, you have to use a lot of training data. Can we reduce the number of training data we use to retrieve the same results? And all these things are very, very interesting and very, very challenging recently. But I think it's a very promising direction if you want to have a go. Okay, that's all.
Yeah, thank you very much, Dr. Zhu. we don't have much time left, but I would like to ask the audience whether there are some questions. So probably I have a little bit question about your last work. That is very interesting, actually, and in the ImageNet, and how, maybe not too much too technical, how many images you found in the ImageNet is like something like a bird is coming, and finally it's something like stripes, lines, textures, and appearing. Are there quite a lot those kind of samples?
Thanks for the question. In the ImageNet, there's many birds. There are many different birds. So bird is one of the major categories. There's many fine-grained birds in ImageNet. But for textures, we found very small amount of images that are related to the textures. But anyway, the model can decide their importance automatically. So ImageNet may be regarded as small because it only has 1 million data sets, and it mainly covers some like general objects. So here I show results on GFT 300 million. So this is an internal Google data sets. So I train their data sets. I train our model on this 300 million. So it has over 300 million images. Those images are noise images, and we train it on bird as well, and we can see that we have a performance of 82.4. This is much higher than the ImageNet. So I think if we are going to do some adaptation, maybe we can use even larger data sets. But I have to say the cost is, for example, ImageNet is 1 million. This data set is 300 million. It's quite a lot and might not work well in academia because we don't have those kind of computational resources.
And also sometimes, for example, ImageNet and some other data set, one image sometimes they have multiple labels. Yes. And for multiple labels, and for example, if some label is bird, some label is something like lines or some other textures, and how do you decide whether there are multiple labels, which one is the most suitable label or fitting, so that you can use that for learning?
Yeah, I think this is a very, very good question. So we didn't consider multi-label case. We didn't directly model the multi-label case, but I think, for example, we are more focusing on the similarity of the visual part. So, for example, we didn't much care about the image labels. For example, if you have multiple labels here, we will calculate the image similarity. We will discount the labels here. We will just measure the similarity of the pixels of the images between the two domains. So we didn't consider the labels. But if there's multiple objects here in the image, I think we may need some modification to have a better alignment. But anyway, if we have multiple labels in single image, then a weight may be decided by the dominant objects.
Okay. Yeah. Any other questions from the audience? Okay. So time is already there, and thank you very much, and we really appreciate that you fantastic talk, and hopefully we can communicate more and in the future research.
Sure. Thanks, Boy.
Yeah, thank you.
Thanks, everyone.
Have a good day.
You too. Bye.
Bye.